linear logic programs are interpreted by smooth functions, and there is a derivation operator in these models. So the idea was to move this derivation operator, which was observed in the models, into the syntax and see what is the meaning of this differentiation. So the differential lambda calculus is made of the standard lambda calculus. You have the variables, the abstraction, and the standard application, which corresponds to composition in calculus. And there is a differential application also, which is a kind of linear approximation of the application of lambda calculus. And it corresponds to the derivation in standard mathematics. So the operator, which is dfxu, is linear in U. It's the derivation in X, which is non-linear in X, but which is linear in U. And there is a similar phenomenon in the substitution that allows to reduce the derivation operator, the linearized application. So let's have a look at that. If you look at the linear approximation of a function using the derivation in calculus, then you have an affine map, which is a linear approximation of f of x. And in lambda calculus, you will have the application lambda x m applied to n, which will reduce by beta reduction to n, where you have replaced every occurrence of x by n. So graphically, if you have this term, lambda x x applied to lambda y x applied to lambda dy, when you apply it to n, you will substitute every occurrence of x by n. Okay, fine. Now, how does work the substitution, the reduction for the derivation operator? You have d lambda x n applied to n, and what you will do is first choose an occurrence of x and then replace this occurrence by n. That means that you need a plus operation for the non-deterministic choice. And also you need to keep the abstraction because there might be some occurrence of x that are still bounded. Okay, so it's a kind of linear approximation of the standard beta reduction. Okay, so what we observe here is that we have two kinds of substitution. One which is nonlinear, where you might have to either to duplicate n or to erase it during the evaluation, and one which is linear, where you will use exactly once n during the evaluation. And this is what we wanted to interpret. And to give a model of it. And to introduce this model, I will first show you a linear, nonlinear, simply typed lambda calculus, which is inspired by words by...
Christine, sorry, I'm going to interrupt because there's a question from Jamie Vickery.
Hi, Christine. Can I ask a question? Can you just go back here to this slide?
Yes.
Could you tell me about the dots? You've got a dot on the baseline and also a dot halfway up. Can you just, obviously the lower dot is variable binding.
Yes.
And is this application?
Yes, it's an application. Can you see my mouse or not?
Yes, I can see your mouse.
Okay, this dot stands for the application. I could have put some just parentheses here.
Because
so
on the line above, you don't use a dot.
Sorry?
On the line above, you have lambda x dot m n.
Yes, yes. It is a different substitution. Here is the standard application, and you can see d something dot something as the linearized application.
Oh, I see. So it is a different. It is application, but it's not the same as ordinary.
Yes, it's not the same. This is the linearized application, and this is the standard one, and the dots is for that.
And what's the affinity of the, I'm having trouble reading that term because I'm not sure about the affinity of the linear application versus, I'm not sure about the relative affinity of these two dots. So I'm not sure how to pass that expression we were just talking about on the left.
On the left, this one?
Yeah. Yeah.
So here, this dot is just to separate the abstraction of lambda x and m. So it's just lambda x m.
Yeah.
Okay. And now I have a term. I could have written dp.q, where p is just a differential term, is a term in my calculus. Okay. Does that answer your question?
Yeah, I can understand that syntax better now. Thank you.
Okay, thank you. So I can go further and present you my simply typed linear nonlinear calculus. So here I have type judgment with two kinds of context: linear types here and nonlinear ones here. The linear types are the typing variables that will be used only once in the reduction, and the nonlinear types are for the variables that can be either erased or duplicated. For the rules of this type system, I have two kinds of rules, the linear ones and the nonlinear ones. We can have a look at this one, for instance. So I have S, which is a function. Its type is given with this funny row, which means that it's a function we use exactly once its input to produce its output of type B. When I apply S linearly, so Jamie, you can remark that I changed my linear application here. I could have put ds.t, but I use this funny bracket to say, be careful, S is a linear, a term of type A, linear map B. So when I apply S linearly to T, the interesting thing is on the context. So here I have two linear contexts, gamma and gamma prime. And when I apply, I just concatenate them. That means that I have no sharing between the variables in gamma or in gamma prime. For the nonlinear context, I will contract the variables. That means that I have kind of, it's like this. I have the substituted term is typed in gamma prime, which is the concatenation of gamma and gamma prime here. And so I have S, which has a linear variable X that I will substitute by T. And for the context, I will concatenate gamma and gamma prime, the linear parts of T and S. And I will just contract the nonlinear variables into delta. Now we can have a look at this nonlinear application. And here there is something I have to be careful at, which is that T, during the execution of S applied to T, during the evaluation, I might have to duplicate T or to erase it. So I cannot say that the linear variables will be used linearly because I don't know how T will be used. That is why I do not allow to have linear variables on here. And for the nonlinear parameters, it's just as before, I use a contraction. So graphically, it's like this. When I substitute in S a nonlinear variable, I have to ensure that the term that will be substituted in U has no linear parameters. One important rule for the semantics is the last one here, which can be deduced from the two sets of rules. And it says that, well, if you know that T is using X linearly only once, then you can feed it with a nonlinear variable X. You know that you will use one. So if you have many copies or if you won't use, if you have many copies of it, it won't hurt. And we will see that appearing in the semantics. Okay, I wanted to make a remark which says that if in the linear rules here, I erase the nonlinear part, then I get just multiplicative linear logic. And similarly, in the nonlinear rules, if I erase the linear context, then I get standard simply typed lambda calculus.
Christine, there's a question from Henry in Montreal. I'll let him ask the question.
Yes, a notational question. I see two arrows on your screen. One is a regular arrow with an arrowhead and the other has an arrow circle on it.
Yes.
What does the arrow circle
So arrow circular is the lollipop of linear logic. And it is to mark the function terms, which will use their inputs only once.
I see. Thank you.
So it's a different type of arrow type, a different kind of arrow type. Okay.
Thank you.
You're welcome. Okay, so now what I want to understand is what is a model of a substitution which combines this linearity and non-linearity. The standard approach is to use a categorical axiomatization. So we take a category which is equipped with the right structure, either a symmetric monoidal closed structure or a Cartesian closed structure. And types are interpreted as objects. To interpret context, we will take this the interpretation of types and we will put them together using either the product or the tensor. And terms are interpreted as morphism, substitution is using the composition, and so on. So for multiplicative linear logic, a term will be interpreted as, of this type, will be interpreted as a morphism from the tensor product of the linear types L1, AL. So graphically, I have my linear types A1, A2, A3. I gather them using the tensor product. I have the right to exchange the types in the sequence of input types, and then I apply a morphism. For lambda calculus, it's about the same thing, but I use a Cartesian product. So I will gather the types using the Cartesian product, and I have the right to duplicate types or to use contraction and weakening, to duplicate types or to erase them. Okay, in interpretation of linear logic, we have this shrink, which allows to move from the linear word to the non-linear word. And it is the same thing to consider a morphism from B1 cross Bn to C, or a morphism, a linear morphism. You look, it is a lollipop here, from shrink B1, tensor shrink Bn to C. And the shrink is interpreted as a comonad on the symmetric monoidal category. And we use this trick to interpret the linear nonlinear lambda calculus with mixed context, the linear part and the nonlinear one. So we gather all the types using the tensor product, and we mark the types which are nonlinear with the shrink. Okay, but here there is a little problem issue, which is that the shrink is interpreted as a comonad, so an underfunctor. That means that I can apply it everywhere. I can put it on the right-hand side just before C, or I can put it before A. I can put shrink L, tensor shrink B1. I can do many things. And we wanted to be very precise and to say that the shrink is only marking nonlinear variables. And that is why we moved to a multi-category setting, and where multi-category is a set of operations which takes a sequence of inputs and which outputs a single input. And this set of operations are coming together with the identity to interpret the axiom, and with a multi-composition to interpret the application. And the multi-composition is working like this. I have a sequence of input here that I will substitute with a sequence of operation. And what I get is only one operation. So here, notice that I have a sequence of inputs. And at the end of the day, I have just a sequence of inputs. And that is why I will need to have a monad to interpret the context, which are this sequence of inputs. Okay, so in a multi-category setting, types are interpreted as objects. Terms are interpreted as multimorphisms, and the substitution is interpreted as multicomposition. So for multiplicative linear logic, a term will be interpreted as a multimorphism in a symmetric multi-category. So graphically, that means that this T will be interpreted as an operation with a sequence of inputs. And I have an operation of the symmetric group on this input. That means that I can exchange the order of the types here. For lambda calculus, it's about the same thing, but a term is interpreted as an operation in a Cartesian multicategory. That means that I have a sequence of inputs here. I have still the right to exchange the order of the inputs, but I have also operations to duplicate the inputs or to erase them.
Christine, there's another question.
Yes.
Jamie.
Thanks, Alexandra. So types, terms, and substitutions. What about contexts?
Contexts are represented by this sequence of inputs. When I am in a multi-category, I don't have to interpret the context, it's built in. You see, my multimorphism is taking already the context. B1, Bn are the sequence of inputs here.
But these B1, Bn, these are objects.
Yes.
So we could say contexts are lists of objects then, perhaps.
Yes, it's about the same thing. But a multimorphism is taking a sequence of objects.
And indeed, yeah, I understand.
Yeah. Okay, so my question is how do I do for my linear nonlinear calculus? So if I want to represent it, I will have to have two kinds of inputs in my multi-category. So an operation will have linear inputs and nonlinear inputs. So I will have mixed sequence of I will have sequence of mixed inputs, either linear and nonlinear, with different kinds of operation. I will have exchange for every types, but also for the nonlinear ones, I will have the erasing and the duplication. And so just for the notation, I will mark the nonlinear types by an underlining, but it's just visually to know of what I'm talking about. Okay, so to give the right presentation of these multi-categories, I will go through the presentation of generalized multi-categories as profunctors combined with a monad for taking care of the context. So in this presentation of multi-category, the multi-category are seen as set of operations. So I have a functor M, which take Tx, which represent the sequence of inputs, which takes a single output in X, and which produce the set of operations of this type. So the context is now represented as a sequence of objects via a monad T on cat. Why a monad? Because here in the multi-composition, I have a sequence of inputs, and I want to produce only a sequence of inputs. So I go from TTX to TX. That is why I need no, it's the contrary because I have a hop here. So that is why I need a monad. Okay, and my purpose now is to know what is the monad corresponding to linear and nonlinear context. Okay, let's go back to the how we interpret things using this presentation of multi-categories. So in multiplicative linear logic, the symmetric multi-category will be represented as a functor from Lx up cross X to set, which is a profunctor with L. It stands for the free symmetric strict monoidal category monad, which take a category and which will produce the free symmetric strict monoidal category on it. And the algebras of L are just symmetric strict monoidal categories. That means that when I apply X to X, I will produce the sequence of objects in X. And on this sequence, I will have built in the action of the symmetric group. Okay, so now a term will be interpreted as an operation living in this N applied to the sequence of objects to C. For lambda calculus, it's about the same thing, but as I just change the monad context. So now I want to have this sequence of objects with duplication and erasing. So what I do is I take the monads that generate freely categories with products, and its algebras are just categories with product. Okay, so this is for linear logic, multiplicative linear logic, lambda calculus. The question is, what is the right monad for a linear, nonlinear setting? So this monad has to produce a sequence of context with the right operations on that. And that is what I want to describe. So can I describe it as, I know how to describe it, but how can I prove that it is a monad? And how can I describe its Q algebras? And for this, we had to introduce a colimit construction, which is the key result in our paper. Okay, so remember, what is a colimit usually? Here we consider only a colimit over one map, lambda from A to B. Then the colimit over it is a cone, C, such that for any other cone, D, here, I will have a factorization through a unique morphism. Okay. But what we will need here is a two-categorical version of these colimits. So I compute the colimit in a two-category, and I will need to relax these colimits by putting a two-cell in it. So now I have the one-cell aspect, which says if I have another codax colimit here, I will be able to factorize it by a unique morphism. And I have also a two-cell aspect that relates when I have a two-cell between two codax cocone. And that says that I have similarly a two-cell between the two factorization. Okay. So I will apply it to this construction to build the monad for linear nonlinear context. And I start from a remark. Every category with product is also a symmetric strict monoidal category. That means that I have a functor from Lx to Mx, and the action on the object is about nothing. It just takes linear types and it transforms it to nonlinear ones. Okay. What we want is that Qx is a symmetric strict monoidal category, because we want to be able to have the interpretation of the exchange rule. Okay, and the object of Qx, we want them to be sequences of linear types and nonlinear ones. The second thing that we want is that we have a kind of embedding of linear types into mixed linear nonlinear types that are just containing the linear ones. And similarly for nonlinear types, I want to be able to take a sequence of nonlinear types and to put them in a mixed linear nonlinear setting. Okay, so the solution is to apply the constructions that I just showed. So I have a map from Lx to Mx, and then I build the collax colimit, Qx. What I get is a two-cell here, which has actually a logical meaning, a logical interpretation. So the component of this two-cell is just a morphism in Qx from this setting with only nonlinear types to these settings with only linear types. And the logical interpretation is this one. It allows me to interpret this rule, which says that, well, T can be typed with using only linear variables. Well, then it's okay to feed it with nonlinear variables because I know that T will use them only once, so it's fine. And it's this morphism here is what we need to interpret this rule. Okay, just a remark here, lambda can be seen as a map of two monads, and it will be important for after. Okay, so I have constructed Q abstractly, and now I want to prove that it is a two monad on cat, and I want to compute what are the Q algebras. I want to characterize them. Okay. The first thing is to observe what are the properties of Qx that I can deduce from the fact that I have one cell and two cell aspects of the universality of the colimit. Okay, so remind that we are computed the colimit in the world of symmetric strict monoidal categories. That means in particular that QX is a symmetric strict monoidal category. That is, it is an L algebra. I have a map from, an L algebra is just a map from LZ to Z, is an L algebra if I have a map from LZ to Z, which is compatible with the units and the multiplication plus some coherences. Okay, so the second thing is QX is equipped with a strictly idempotent comonad. And what this comonad is doing is taking a mixed linear, nonlinear sequence of types. It will produce the same sequence, but regarding every types as nonlinear ones, as nonlinear types. And of course, if you apply it the second time, because you have only nonlinear types here, when you do it again, you just get the same thing. That is why it is idempotent. And there is a 2 cell from F to the identity, which again has the same logical meaning, which says that if I know that T is using a linear variable, then I can just feed it with nonlinear ones. Then QX is a category with almost products, almost with products. That means that I have a left semi-M algebra that is a map from MQX to QX. It is not really an M algebra because the unit law is not satisfied. It's satisfied up to a 2 cell. And this induces 2 left semi-L algebra that are equal. Okay, fine. I can prove that I have these properties, and actually it's very important because this will allow us to characterize the algebras of Q. So I define a new category, a 2 category, which is the structure category, and this is the description of the objects of this structure. It's exactly the properties that I have just showed on QX. Z is an L algebra. It is almost with products, so it's a left semi-M algebra, and it's equipped with an idempotent, strictly idempotent comonad, which induce 2 left semi-L algebras which are equal. And of course, QX is one object in this structure category. Okay, so now I can state my theorem, which says that if I have a map of 2 monads on cat, so if L and M are 2 monads, and the L algebras as colimits, then I can compute the colimit, the Colax colimit in the 2 category of L algebras, which is this one. And I can prove that the Q algebras are objects in the structure categories that I just described, and Q is a 2 monad on cat. And I prove the two properties together. And for this, it's important that I'm using the universality of the colimit, which is the important fact is that I am using the unicity in the colimit. Okay, so it's a nice mathematical structure I want to use now to describe the linear and nonlinear substitution. Yes.
Sorry, Christine, could I ask a quick question?
Yes.
Could you give me some
yes, of course.
Intuition for this structure category? What role is it playing here? What's it encoding?
So this structure category. So the role in the proof here is I have several steps. The first thing is to prove that QX is a structure category. Then the map I can to prove that Q is a 2 monad. I have to prove that mu I have to build the multiplication for the monad. And I use the fact that this multiplication is a map in the structure category. And so it's a little bit hard to explain why it's the role of this structure category in the proof, but we are really using every part of the category, the object, the one cell and the two cell, to prove both that the structure of the two monads is working and that the Q algebras are really characterized by the structure category.
I mean, I wonder if this structure category is analogous to other sorts of structures, that categorical structures we might build traditionally for type theories. I'm having some trouble. It seems like a very natural object, but I'm having trouble knowing how to think about it intuitively.
Yes. So one thing I can do to answer this question is to go a little bit here. So I'm sure you know about the linear nonlinear adjunction that allows to interpret linear logic. And Jamie, you can answer to that?
Yes. Sorry,
yes.
I was muted. Yes.
Okay, so from a linear nonlinear adjunction, I can build a structure category. So imagine you have X, which is for the strict symmetric monoidal word, so the linear word, and Y is for the nonlinear word, so it's a Cartesian category. And I get rid of the plus structure because it's an orthogonal problem. So here I have an adjunction between S and R, which is a monoidal adjunction. And I can build a structure category, or almost a structure category. I will say a word about that afterward. So how do I do that? So X is a symmetric strict monoidal category. So I have, it is an L algebra, okay? It's the first ingredient. Then Y is as products. So it is an M algebra. And from it, I can build a left semi-M algebra by just pre-composing and post-composing by the two parts of the adjunction.
I think in a linear nonlinear adjunction, we don't normally have X being strict, do we? That's standard?
Yes, I think so.
Okay.
So here it's MR, and I can just compose. Okay, and now this idempotent comonad is here. I just do R and S and I get the shriek. And from what we know from the interpretation of linear logic, we just get what we wanted. We have the interpretation as a symmetric monoidal category, and we have the Cartesian category, and we have the shriek. But here, this is just, how to say, it is not exactly the same thing, but it gives you some intuition on what's happening. So the structure category is just describing what are the ingredients we need to have a linear substitution and a nonlinear one living together. So if I go back to this structure category, I have the thing to interpret the linear word, the thing to interpret the nonlinear one, and we know how to relate the words through this idempotent comonad, and the fact that the two left semi-L algebras are corresponding. Okay, so
okay,
I'm not sure.
That's helpful, thank you.
Okay, thanks. Okay, so now when I apply this construction to L being the left, strict symmetric strict monoidal category and the two monads for linear context and nonlinear ones, then I can produce the linear nonlinear context monad, and I can prove that it is a two-monad uncut, and I can characterize the structure category, which was the problem that I was asking at the beginning. But it is not the end of the story, because if I want to describe generalized multicategory for linear nonlinear substitution, I have to prove that Q extends from cat to prof. Why? Because if you look at multicategory as a profunctor, so this is a notation, just M is a profunctor from X to TX, where T is the monad for the context. This is a notation for M being a functor from TX up cross X to Z, which was the definition of multicategory I get. Okay, So the multi-composition, you take an operation in M, and you take a sequence of operation, which is actually in Tm. That means that I am applying T to prof and not to cat. So I have to extend T from cat to prof. And to do that, I can use the pseudo-distributive law, which says that to know that Q extends from cat to prof is equivalent to prove that the preshift pseudomonads lift to pseudo Q algebras. Okay, and that is work in progress. What we want to do is to prove that the preshift pseudomonad lifts to pseudo Q algebras. So if I take a Q algebra, I apply to it the preshift pseudomonad that I want to prove that I have a pseudo Q algebras, a pseudo Q algebra. But well, to describe what are the pseudo Q algebra, I have to give a characterization of it. And what we conjecture is that pseudo Q algebras are just a pseudo version of the structure category. And the problem is that to prove that that Q algebras were corresponding to structure categories, we were using this universality of the colimit. But pseudo Q algebras will be pseudo L algebras, and we are in symmetric monoidal categories, and there is no colimit in the two categories of symmetric monoidal categories. It's not co-complete. Why? Because the tensor product is not strict anymore. So we won't have the unicity of the factorizations for the cone. So the trick we want to use is a strictification to go from symmetric monoidal categories to symmetric strict monoidal categories to recover colimits and to finish the work. Okay, so the next thing that I just presented you is how do we relate to usual categorical axiomatization of linear nonlinear substitution. And for the straightforward thing that we can do, which is to try just to produce the structure that we need, is not working, because the first, the comonad that we get is only lax, is not living in the symmetric strict monoidal category. And furthermore, the two left semi-L algebras are not corresponding. So what we think is that we can recover a structure category, but by going through multi-categories, and it will be another work. And finally, my first purpose was to present an axiomatization of differential lambda calculus. So if I am able to describe linear and nonlinear multicategories to interpret linear and nonlinear substitution, then I have still some work to do. The first thing is to present, to know how to interpret variable binding. And for this, I need a closed structure, which allows me to turn an operation with n+1 inputs to an operation with n inputs. Because when I do the binding, I just get rid of one of the inputs is not appearing anymore. The second thing is to interpret the derivation operator. And for that, I can use the differential interaction nets or their categorical version as a guide, because what I will have to do is to describe this derivation operator, which takes a nonlinear variable and which takes an operation with a nonlinear variable and which produce another operation in which this I have two new inputs, one which is linear and one which is nonlinear. And the last thing that I will have to do is to understand how this operation is working with the contraction, which is needed for the general. And then I will have to add some additive structure because the derivation of the contraction will need some non-deterministic choice, as I presented at the beginning. Okay, so to conclude, I just put this famous sentence of Dijkstra, which says that the purpose of abstraction is not to be vague, but to create a new semantic level in which one can be absolutely precise. And I chose this sentence because this work might seem just to be interesting for the love of abstraction, but I think it will give us some insights on what is the linear nonlinear substitution that appeared in differential lambda calculus, but that appear also in other contexts such as quantum computing or other reactive systems and so on in many places in computer science. And I believe that by understanding more precisely what is this linear nonlinear substitution by using this multi-categorical setting will allow us to uncover some logical features of this kind of systems. And this is the end of my talk. Thank you for your attention.
Okay, thanks, Christine. Great quote at the end. So I'm going to unmute everyone so that we can thank Christine. See, it should be, yeah, everyone should be able to. So, okay, so now we can take we have some time for questions. Let me just see if someone has raised their hand.
Can I ask a question?
Yeah, go ahead, Jamie.
So in the traditional setup of this linear nonlinear model, which you recalled, we don't use the theory of multi-categories, right? We have monoidal structures. Can you explain why multi-categories are essential for the development that you're making, right? From any multi-category, we can generate a monoidal category if we want to.
Yes.
So why did we have to leave the world of monoidal categories in order to do what we're doing here?
Okay, so in the world of monoidal category, if I want to recover the nonlinear parts, I need to have this trick or this adjunction if you want. And that means that I can put this trick everywhere. So what we wanted really to do was to be really precise and to say exactly what are the nonlinear inputs and what are the linear ones, and not to have a system where I can put this trick everywhere. This is something that you can remark if you are working with proof nets or interaction nets, where you have this Schwick cell which is interacting everywhere, and we wanted really to describe the substitution which is working here, which is here, and to focus on it. So we moved to the multi-categorical setting because we were interested in describing this this substitution.
Okay.
So what I'm saying is you have too many morphisms if you are in the using the categorical axiomatization.
Okay.
Okay, we have a question from Gordon Plotkin. Gordon, I think you're muted.
Yeah, I just got told that by Zoom. Sorry. So following on Jamie's question, another way to go perhaps would be to use a generalization of categories, in which instead of having a single domain, you had two domains for your morphisms, one for linear, one for nonlinear. Then you could avoid multi-categories. Yeah. That's my question. Yeah.
So you want me to avoid multi-categories? That's
well, I'm just helping Jamie. You would still avoid the banks and things because you.
Okay, so can you say it again? You propose to have two kinds of inputs?
Yeah, I'm sorry. No, yes, I'm supposed to just to generalize the notion of category, but not quite so far.
Okay.
So instead of HOMS having a domain and a codomain, you'd have two domains. A
Yeah.
linear one, you see what I mean?
Yes. So I'm not sure how to do that, because then you might still need for a tensor product on a Cartesian product if you want to have to combine the two things, and you might have something to move from the linear worlds and to non-linear worlds, which were very important in what I presented here.
Yes, but you can still do it, I thought. Anyway, just a thought.
Yeah. I don't know, I have to think about that, but well, it's also a matter of choice. Actually, we wanted to use multi-categories, and we were happy to see that this colimit allows you to give accounts of what's happening to context, to the context monad. So it's another way to describe how to mix the linear context and the non-linear ones.
Sure, yeah, no, it's very nice from that point of view, of course.
Okay, I don't see any more questions for the moment, but people will have the chance to ask more questions to Christine during the coffee break. So what will happen next is the people who stay in the call, I'll split them into groups for the coffee break, and then eventually everyone gets to move to Christine's room. So if you don't want to stay in the coffee break, then you should leave in a moment after we thank Christine again. But otherwise, I suggest that people turn their camera on so that we know they're here, and we will move straight away to the coffee break. So yeah, thanks once again, Christine, for this nice talk, and we'll move on to the coffee break. Thank you.
Thank you.